Humanity has always gazed at the stars with curiosity, but now we're actively pursuing a future among them. Establishing permanent colonies on the Moon and Mars is not just a dream, it's a necessity. Whether it's ensuring the long-term survival of our species, unlocking scientific discoveries, or catalyzing new economic opportunities, space colonization is both visionary and feasible. But how realistic is it? And what are the steps we need to take to turn it into a reality? Why colonization matters, the case for the Moon and Mars. Before diving into logistics, it's crucial to understand the why behind the push for colonization. Ensuring human survival. Natural and man-made catastrophes, asteroid impacts, nuclear conflicts, or devastating climate change pose existential threats to humanity. Establishing colonies beyond Earth could provide a backup for civilization. This isn't a doomsday plan, but rather a proactive step toward ensuring the continuity of our species. Scientific discovery, permanent settlements on the Moon and Mars would revolutionize science. We could explore the geology of celestial bodies up close, study the origins of the solar system, and even search for signs of life. Mars, with its history of water and potential for past microbial life, offers unparalleled scientific opportunities. Economic and technological growth colonies could become hubs for resource extraction, such as mining the Moon's regolith for rare minerals or Mars' subsurface ice for water. Innovations in life support systems, energy production, and construction will also advance technological capabilities on Earth. Why colonize the Moon and Mars? The Moon, a gateway to space and Mars. The Moon is not just a stepping stone. It's an essential platform for deeper space exploration. Proximity. At about 384,000 kilometers away, the Moon is only a 3-day journey from Earth. This makes it ideal for testing human endurance and technology needed for more distant missions. Resource potential. Lunar regolith contains valuable resources like silicon, aluminum, and oxygen. More importantly, the poles hold water ice, which can be used to produce drinking water, oxygen, and hydrogen fuel. Test bed for technology. Lunar bases offer a lower-risk environment to test life support systems, closed-loop habitats, and other technologies critical for Mars colonization. With just 1/6 of Earth's gravity, the Moon serves as a manageable proving ground for space-based living. Mars, the long-term goal. Mars presents a different but more ambitious challenge: potential habitability. Mars has a thin atmosphere composed mostly of CO2, which could be utilized for growing plants through greenhouse cultivation. It also has abundant water ice and a 24.6-hour day-night cycle, making it relatively Earth-like for circadian rhythms. Terraforming potential. Over centuries, Mars's environment could be gradually altered to support more Earth-like conditions, creating a foundation for long-term human habitation. Roadmap for colonization. Key phases. Phase 1. Establishing sustainable presence on the Moon. Robotic exploration and preparation. Robotic missions are crucial for identifying suitable base locations, mapping water ice deposits, and assessing radiation levels. NASA's Artemis program, along with China's Chang series, are already conducting lunar missions aimed at preparing for human presence. Initial habitat construction. The first lunar habitats will likely be modular and inflatable, shielded by lunar regolith to protect against radiation and micrometeorites. Modular bases, inflatable habitats covered with regolith, offer a low-cost, efficient way to establish initial human presence. 3D printing. Technologies that utilize lunar regolith for 3D printing building materials are under development. The European Space Agency, ESA, has tested 3D printed bricks made from simulated lunar soil, which could be used for habitats, landing pads, and roads. Radiation shielding. The lack of a lunar atmosphere means settlers will need extensive protection against cosmic rays. Underground habitats, regolith-covered domes, and specialized materials are all under consideration for shielding purposes. Resource utilization and energy solutions. In situ resource utilization, ISRU. Water ice extracted from the Moon's poles can be converted into drinking water, oxygen, and hydrogen. Oxygen can also be extracted directly from regolith, reducing the need for supply missions from Earth. Energy solutions. Solar energy is the most feasible power source. Solar panels installed at the Moon's poles could generate continuous power. Additionally, compact nuclear reactors, like NASA's kilopower, could provide stable energy during the lunar night, which lasts about 14 Earth days. life support systems and food production, closed-loop systems. Effective recycling of water, air, and waste is essential for sustainability. Algae-based systems can help produce oxygen while recycling CO2, and hydroponics can provide fresh food. Greenhouses. Lunar greenhouses could utilize hydroponic or aeroponic growing techniques, relying on artificial lighting to cultivate crops within a pressurized environment. Phase 2, launching the Mars Initiative, preparation and launch infrastructure. Orbital outposts. The Lunar Gateway, planned for the early 2030s, will serve as a staging ground for Mars missions, allowing for assembly, refueling, and crew acclimatization before the journey to Mars. Crew selection and training. Astronauts will undergo intensive training in survival, self-sufficiency, and teamwork. This will include isolation simulations and practice in handling Martian gravity, about 1/3 of Earth's. Mars landing and base setup. Landing site selection. Likely initial sites are equatorial and mid-latitude regions with subsurface ice deposits. The Mars 2020 Perseverance rover and future missions are scouting potential sites, particularly in areas like Jezero Crater and Arcadia Planitia. Initial habitat design. The first habitats will be pressurized modules buried under Martian regolith to protect against cosmic rays and temperature swings. Local resource extraction. Extracting water ice will be the first priority. Water will not only be crucial for sustaining life, but also for generating fuel, hydrogen and oxygen via electrolysis. Energy solutions for Mars solar power. While feasible, solar power on Mars is affected by dust storms and reduced sunlight intensity due to its greater distance from the sun. Dust-resistant panels and enhanced battery storage will be key. Nuclear power. Small modular reactors, such as NASA's Krusty kilopower reactor using Stirling technology, are essential for providing reliable energy independent of solar conditions. Sustainable food production, hydroponics and greenhouses. Crops can be grown indoors using LED lighting and nutrient-enriched water. NASA has demonstrated plant growth in simulated Martian soil, showing potential for local agriculture. Resource recycling. Efficient water recycling, waste composting, and air purification will be vital for maintaining life support systems. Challenges to overcome. The harsh realities. 1. Radiation hazards. Moon. Without an atmosphere or magnetic field, the Moon offers no natural protection from harmful cosmic rays and solar radiation. Structures must be shielded with regolith or constructed underground to provide adequate safety. Mars. Though its thin atmosphere provides slight protection, Mars' weak magnetic field still exposes colonists to dangerous radiation. The proposed solution includes thick-walled habitats, strategically placed below the surface or covered by several meters of regolith. 2. Gravity's impact on health. Low lunar gravity, at 1/6 of Earth's gravity, the Moon presents long-term risks like muscle atrophy and bone density loss. Regular exercise regimens and potential use of rotating centrifuges in habitats could mitigate these effects. Mars gravity, at 1/3 of Earth's, is less severe but still poses health challenges. Simulating Earth-like gravity during transit and developing robust physical conditioning programs will be necessary. 3. Psychological and social challenges. Isolation, delayed communication, up to 20 minutes one way to Mars, and confinement could lead to psychological stress among colonists. Solutions include structured schedules, keeping a regular daily routine that includes work, exercise, and leisure activities. Artificial reality, AR, and virtual reality, VR. These technologies could help colonists feel more connected to Earth, reducing feelings of isolation. Support systems. Counseling and real-time AI-based mental health support could play a crucial role in maintaining emotional well-being. 4. Cost and political hurdles. Funding needs. Building and maintaining lunar and Martian colonies could cost hundreds of billions of dollars. International collaboration and private sector investment will be crucial to cover costs. Geopolitical concerns. The legal frameworks governing space resources and settlements are currently vague, requiring new international agreements to ensure peaceful and ethical exploration. Future outlook. How realistic is colonization? Colonizing the Moon and Mars is not a question of if, but when. The Moon could have its first permanent base by the 2030s, serving as a launch pad for Mars missions by the 2040s.